In this lesson, we're going to start talking about system design with respect to air distribution. Now, air distribution, we're talking about ductwork, we're talking about the blowers, we're talking about anything that is moving the air either into the system, out of the system, or for ventilation purposes around a conditioned space or building. So, let's start off with a brief introduction. Air conditioning systems condition air and distribute it through a space. They're designed to distribute air to the proper space in the amounts that provide the most comfort to the occupants of the conditioned space. Now, by comfort, we're meaning temperatures, humidities, drafts. Okay, all of this has to be taken into account. A good air conditioning system delivers clean air to the space being conditioned. Proper ventilation is also important because it can help control humidity levels in indoor spaces. Uncontrolled humidity from bathrooms and laundry rooms can cause condensation on windows and walls. Proper ventilation can also control odor from cooking, smoking, or other household activities. So you can't have a building without ventilation. Ventilation has to happen, and in most jurisdictions, ventilation is code now. Before designing or installing an air distribution system, the basic properties of air must be understood. If you don't understand these properties, the behavior of air will result in a poorly designed system. Some of the properties of air are to consider are air has weight. Air absorbs heat, and we have to understand how it absorbs heat. Air separates into layers based on different heat levels, and temperatures, which is called stratification. Air has a definite weight, even though it is invisible. The gases that compose air have a definite mass and therefore has a weight. 1 pound of dry air at 70 degrees Fahrenheit at standard atmospheric pressure occupies a space of 13.35 cubic feet. That's an important thing to remember. 1 pound of dry air at 70 degrees Fahrenheit at standard atmospheric pressure occupies a space of 13.35 cubic feet. At 50% humidity, 1 pound of air and moisture mixture takes up 13.51 cubic feet of space. As the temperature rises or pressure, air expands to fill a greater space, and as it drops, air contracts. Now, again, this is called a temperature-pressure relationship. As the relative humidity increases, each pound of air will occupy a greater space. There's two types of heat that can be added or removed from air. We have sensible heat and we have latent heat. When sensible heat is added into air, an increase of dry bulb temperature occurs. When sensible heat is removed, there's a decrease in dry bulb temperature. The latent heat in the air is the amount of heat that would be released if all the moisture in the air was condensed out of the air. Since colder air is not capable of holding as much moisture as warmer air, the air is much drier during the winter season. A humidifier is used to add moisture to this air. Moisture is commonly added while air is being heated to bring the air as close as possible to the human comfort level, which is approximately 70 degrees dry bulb with 30% relative humidity during the winter months. Again, human comfort level in the winter months is about 70 degrees dry bulb and 30% relative humidity. Remember, at any temperature, the more humidity in the air, the warmer you feel. The less humidity in the air, the cooler you feel. Relative humidity compares the air that is being treated to the same air that is completely saturated, in other words, wet, with 100% relative humidity. Saturation is the point at which no more moisture can be added to the air without it raining. Okay? Absolute humidity is the actual amount of moisture in the air. The moisture content is often expressed in grains of moisture per pound of air. There are 7,000 grains for every pound of moisture. The evaporator coil in a cooling system removes both sensible and latent heat from the air in regions that maintain higher relative humidity levels during the summer months. For each pound of moisture removed from a coil, about 970 BTUs will be removed from the air. BTUs, remember, is how we measure heat content. And just to give you an idea, 12,000 BTUs equals 1 ton of air conditioning. So for each pound of moisture that's removed from the coil, there's about 970 BTUs being used, and this is latent heat. As both the sensible and latent heat decreases, the air will move closer to its indoor target design dry bulb temperature of about 75 degrees and a relative humidity of 50%. Remember, anything over 50% relative humidity, we take a chance in growing mold. So we want to maintain our relative humidity in indoor environments under 50%. Now that's tough to do in parts of the country. For example, in Florida, it's very difficult for us to hit a 50% relative humidity in the summer months inside. Okay, a lot of our cooling goes to removing moisture. In a given space with no drafts, warm air tends to rise and cold air tends to fall. This is called stratification. If the air is not deliberately moved, the air will settle at different heights according to temperature. To prevent stratification, the air in an occupied space must be kept moving. Because again, you're going to have different levels of comfort. Cold air will fall. So we don't want all the air-conditioned air just to be around the floor. Because most people will feel that cool on their feet, but the rest of the bodies will feel warmer. So we have to actually move the air in conditioned spaces. If a thermostat or humidistat is placed too high on a wall in a room, it will be exposed to air that is warmer and more humid than the air felt by the occupants. If the thermostat or humidistat is too low, it will be exposed to air that is cooler and less humid than the air felt by occupants. Thermostats and humidistats should be mounted approximately 5 foot off the ground. Proper placement of supply and return grills is also important. Poor placement of these components could cause the air to move in certain parts of the room while becoming stagnant in others. Furnishings that are in rooms can obstruct air movement. To minimize obstruction caused by furniture in a home or office, duct outlets are often placed high up in the room or in the ceiling. Okay, this picture is just an example of ceiling diffusers around a kitchen or living room environment. Keeps it out of the way of the furniture. Okay, what they're not pointing is right where my mouse is, there's a return grill. So we have our outlets, our diffusers that the supply registers. Air is coming into the space around the four corners. It's going to diffuse, cause currents to go on the ground, and then it's going to come back up into the return grill that's sitting right there. Again, gets rid of stratification because we're moving air in all parts of the room. In warm air heating, 3 systems are used to circulate the air. We can use gravity, we can use intermittent forced air, and we could use continuous forced air. By the way, these are the same in air conditioning. The gravity system is no longer popular because of the energy being lost before the conditioned air reaches the room. Most installations use intermittent forced air systems, where a thermostat controls the blower fan in the air handler. The thermostat turns on the blower whenever the sense temperature becomes too far above or below the set point. Continuous forced air systems are also growing in popularity. They provide a more constant temperature in the rooms. The difference is that the continuous forced air systems, the fan runs constantly. Air distribution systems are designed to provide cooling as well as heating, and they may need the ability to move different volumes of air depending on the mode of operation. A cubic foot of cooled air will not change the room temperature as much as a cubic foot of warm air. This is because the greater temperature difference is being produced. In the average conditions, a 30 to 50% airflow increase is required between heating and cooling modes. Either of the following two methods can be used to increase the airflow. We can use a 2-speed or variable speed blower motor, or we can use an adjustable pulley system for belt-driven blowers. More and more, you're not going to see the pulley system in light commercial or residential. We are using variable speed blower motors, and more you're seeing ECM or electronically communicated motors. Air entering a conditioned space through ducts must circulate without causing annoying draft. Air circulation depends on the number and the size of the duct supply outlets and return inlets. It also depends on the velocity of the air moving in the duct. Air delivered to the room from a supply duct is called the primary air. Primary air pushes against and mixes with air as it leaves the duct outlet. The distance the air travels from the duct before it slows to 50 feet per minute, or FPM, is called the throw. The throw is how far the air travels from the duct before it slows down to a rate of 50 feet per minute. On the return ducts, airflow through the return ducts is almost always caused by the pulling action of a blower. If the return airflow does not match the airflow being supplied to the room, the airflow is not properly balanced. If there's more return air than supply air, the room will have a negative pressure, and this condition is commonly termed starving for air. Rooms that are starved for air are usually cold during the heating season and warm during the cooling season. To correct a starved room, more supplies must be added to the room. Return duct inlets should be placed in a stagnant air zone of a room. During the heating season, returns would be located near the floor. Remember, cold air falls. We want to pull the cold air out of the room. During cooling seasons, these are usually located near the ceiling. Okay, this design is not always practical due to cost. A lot of times we do have to pick one or the other. So you look at what you do more in the space. Are you heating or are you cooling more often? Therefore, placement of the return duct inlet is determined by the type of construction of the building or whether the primary use of the system is going to be for heating or cooling. In all cases, the return duct inlets should be located at the furthest distance from the supply duct outlet. So again, this is just a cutaway of an attic system. We have our air handler, we have our supply plenum, and we have our return plenum. Now if we take a look at this is probably not the best design because we have our supply ducts that are coming, our supply plenums coming out, okay, and then we're branching into a number of different locations. But you notice this only has one central return duct. Okay, so all of these rooms over here, when you close the doors, you suddenly have supply with no return. That's not the best design. Okay, so we want to have as many returns as we can possibly have. Okay, but you do see a lot with the central return systems. We have some basic ventilation requirements. Now, ventilation means intake of outside air. Air normally contains about 21% oxygen, and people need a certain amount of oxygen in the air in order to breathe comfortably. If the oxygen content falls in a room, people can experience issues such as discomfort, breathing difficulty, drowsiness, disorientation, and if it's bad enough, unconsciousness. As oxygen is consumed by the occupants, carbon dioxide, water vapor, and other impurities increase. As the oxygen decreases, carbon dioxide levels increase. People may complain of the room feeling stuffy. It's for this reason living spaces must have air with sufficient oxygen content. It's very important that air be admitted to provide necessary oxygen. Otherwise, you have what we call a stale environment. In the past, fresh air entered the structure by infiltrating through doors, windows, and cracks in the structure. Modern construction techniques have reduced this greatly. Therefore, modern air conditioning system must furnish fresh air. Modern AC systems should have controlled fresh air intakes. These intakes mixes outside air with the conditioned air. And this is just an example of this, okay? We put a fresh air intake damper that's just a path to the outside, looks like a dryer vent on an outside wall, nothing around a driveway or a road. We want it in an area where we're going to get as clean air as possible. We pull it into our return duct just through the pressure of the return duct. We clean it, we filter it, and then we push it out through the blower, through the coil into the house. Okay, so what we're doing is we're bringing in a little bit of return air into the building at all times. A little bit of fresh air makes a big difference. Fresh air can be brought into a space by using fresh air duct connected between the outdoors and the return air ducts. We can also bring fresh air from the outside by using a heat recovery ventilator, HRV, or an energy recovery ventilator, ERV, depending on what part of the country you're in. When fresh air is brought into the space by the AC system, a positive pressure can be maintained in the building. This will help keep out airborne dirt, dust, and pollen. Positive pressure basically says the building has a air pressure above the atmospheric pressure found outside. Negative pressure is below the atmospheric pressure outside. Negative pressure should always be avoided in a building because it reduces the efficiency of exhaust fans and exhaust from fuel-fired appliances. We want to avoid negative pressures at all costs. Always want to keep things at a positive pressure. Two examples of this, okay? So if we have a positive air pressure in a building, okay, cracks and crevices around walls, windows, and everything else like that it's going to push air outward. So if I hold a flame up next to a crevice or a window or an outlet, we're going to feel the air pressure going outwards, okay? It's going to be pulling the flame to the wall. If I do the same thing in a building with a negative air environment where we don't have fresh air intake and it's a tight building, okay, we're going to find out that the flame is going to want to pull in, okay? So we're going to be pulling dust, dirt, and everything else in, and our chimneys and our exhaust fans won't work as nicely as they did in a positive pressure environment. Air changes need to be calculated by counting the people in a building or calculating the volume of the space. To calculate fresh air requirements and air changes per hour, the following factors must be considered: number of occupants, the use of the space, the dry bulb temperatures, the relative humidity, the amount of fresh air emitted by infiltration, and the efficiency of the unit. A system in cooling mode should provide at least 15 CFM of air per person. That's 15 cubic feet per minute of air per person in the building. Okay, formula for calculating required air exchange is actually relatively simple. The required air exchange rate is the number of occupants times 15 CFM. The formula for calculating the time required for the complete air exchange is the size of space divided by the air exchange rate, and that will give you the time for complete air exchange. And again, size of space is volume, so it's in cubic feet. Okay. So this is a chart that's out of our code books, okay? Again, formula for calculating air exchange rates per hour. 60 minutes divided by time for one exchange equals air exchange rates per hour. So a type of space would be like a home, office, or public assemblies. If we're in heating mode for houses, we want 3 to 6 air exchanges per hour. Okay, office spaces, we want 5 to 8. Public assembly areas, we want 5 to 10. This is usually based on the amount of people. Now in cooling mode, it is higher. We want 6 to 9, 6 to 12, or 6 to 12, respectively. And again, this has to do with moisture, humidity, and everything else. Now, once again, it is very important to check current code for your area and whatever jurisdiction you're in to make sure you're following the current code for this. Energy efficiency, building codes, and everything change per state and actually parts of the country. It's good practice to leave air blowers running all the time as they provide good ventilation to all parts of a building. This is especially important in commercial buildings. In residential environments, if you have a ECM motor that provides a low flow, just air movement, and if you have very well insulated ductwork, especially in an attic, you have to have really well insulated ductwork to be able to do this, or you start pulling in a lot of heat from the attics. So that is basically what we can look at about our basically ventilation, air movement, air flow. Again, important things to remember: air has weight. This weight of air takes work to move. Okay, air will stratify if the air is not being mechanically moved. Okay, hot air rises, cold air falls, and we have to take that all into account when we place ductwork and calculate air requirements. You have to pull ventilation in from the outdoor environment and check your codes to see how much.